Hi there, Michael.
Hello.
Hi there.
Hi, Brendan. Can you hear me fine?
I can hear you, but I can't see you.
Yeah, I haven't turned on the video yet. Let's try that. Might be a little dim in here. Okay,
Hi there.
let's see. Okay. I heard a beep. That was my oven. That was just telling me that it was up to temperature. I don't have to worry about it. Am I coming in loud and clear, or is it too
Yeah, you're
soft?
coming. You're coming in reasonably good.
Okay, good. Good.
Did you see the
I
email
uh,
by David?
I just saw that. I wanted to get the end of the meeting, so I didn't quite read it all the way through yet. But I saw him link to the 1D stepper.
Yeah. Paul Laviolette said that it sent me an email saying that it would be a bit late for him. It'd be about 11 o'clock in Greece, I think. So for next week we could go back to we could go to 7 p.m. GMT, which would be like 2 o'clock at your end, I think.
Or 3 o'clock where I'm at. Yeah.
All right.
Hmm.
And then
I
we'll probably join the meeting then.
I don't know. Maybe with the time difference, with the your daylight savings, maybe it would be. I'm not sure. It's confusing.
Yeah,
Yeah.
yeah. So 7 o'clock GMT is an hour earlier.
Okay. So what time is it over there right now?
Well, here it's 9 o'clock.
Okay. So it's a 5 hour difference for me. Yeah. It
Did
used to
you?
be four. So that makes sense.
I'm not sure if I haven't heard from Justin. So David Johnson's probably going to be a bit late. He said something like let me see if I can find it here. That he might be late again today.
I
So
saw that. Well, I thought that was pretty interesting that I had he what did Matt give him special permission to use that software, or was it already up there?
I think it was already up there, but David asked permission from Matt.
Okay,
He says it looks simpler anyway. I've had a quick look at it.
I was
Um,
going to take a peek myself,
I,
but I don't know if there's anything that you've been working on that I can
yeah, I can
take.
I can share some. I can share some this screen with. Can you see that?
Not yet, but maybe soon.
Can you see it?
Something's happening. My computer may be a little on the slower side
What
right
if I
now.
stop the share and do
Well,
it
I
again?
see it now.
Can you see it
Yeah,
now?
yeah, but then it went away.
Can you see
There it
that?
is. Yeah.
Okay, let's just this is the thing. This is the update I wrote on. Whoopsie. Let's go. This is the update I wrote, and I wrote a little introduction to the method, the what do you call it? I've forgotten the name of it now. Krunj-Kuta method.
Yeah, I remember hearing it here in the States. I've heard it called Runga Kutta.
So I just wrote a little thing here: exponential time differencing and the Krunj-Kuta method, solving
Yeah.
PDEs in Model G. So I mean, if we go over to David's simpler model, which might be easier to change and might be easier to write as well. But
Oh, you
anyway,
mean
I
the
just I
Matt's
just
1D?
yeah, it's 1D at the moment. He thinks he can upgrade it to 3D, and he thinks it might run faster. So he was saying just use something simpler. If we use something simpler, then it'll be easier to write, and even if it takes longer, it doesn't matter as long as it's more easier to access. So
Huh.
this is just. Can you see this method here? It's basically this is from Wikipedia. So it's just taking an equation like this one here, which is a time and distance function of t and y, and you calculate the k values, k1, k2, and k3, and then this is like the curve here, and they're calculating them, and down here is the code from Matt Pulver's ETD stepper, basically calculating the k values. So that's what I worked out for the k values there.
Okay.
There. Hi there, David.
Hello.
There, and there, and there.
I have no sound here.
We can hear you.
Can you hear us?
I have to chat.
You can't hear us. Why didn't you take the sound out and put? Why didn't you refresh the screen? Refresh the screen. I'll try. Let me just try doing this. What if I do?
Hello.
Let me just see.
Hi there, David.
Oh, there's.
Can you hear me? I cannot hear anything. Very strange.
I'll write it here. Refresh screen.
Hi, Justin.
Hi, how are you?
Hi there, Justin.
Can you hear me?
David. I was just sharing this update I did on the report on the academic note. It's just a collection of notes, really, but I looked at Wikipedia, and I found this. They're showing for the what's it called, Krunge-Kuta method, which is used with exponential time differencing and the Krunge-Kuta method for solving PDEs in Model G. And so that's a sort of graph of how it estimates the curve. It makes estimates with a kind of iterative technique. I just took this from Wikipedia, which basically shows, okay, so here's some kind of function here, a function of y as a function of t and y. That's the that's what your estimate is, and these are the values of k1, k2 to k4, and this is the ETD stepper where Matt was solving these k values here. So we can see he's got phi there and phi h there. So here we go from k0 to k4. So it's just a note. It's just an academic note. It's not. I'm not to help with ideas of what to do next. And I also altered this one here. Can you see this term here? I realize that's would just be G. This here would just be G. Can you hear us now, David? Okay, let's just
Well, he's been able to. Oh no, yeah.
well, we can put it in the just put it in the notes. Where is it? Stop share. Where are the notes? Chat.
Well, it sounds like we're making pretty good progress on the 3D stepper. I mean, the 1D could be useful for a lot of things, but I'm not sure from what Matt was saying that it can be extended very well without using way too much time. But
okay, well, I'll share that. I'll share that. That's the.
Can always be given a try and to see.
Justin's just left us for.
Sort of, yeah.
So here it is here.
Yeah.
And this is it. It's just this size here. It's not a very large program. That's all it is. Okay.
Hmm.
What's happened to Justin then? Has he just left us?
Well, either that or he's become transparent. One of the two. He's lost all of his pigmentation.
Sorry?
Oh, it looks like Justin has lost all of his pigmentation.
Yeah.
He's become transparent.
So did you see Paul Lavillette's note there? He just replied. Just reaching out.
Oh, yeah, I saw that.
Okay, we better not.
Has Dr. Paul,
Hi there, David.
yeah. Maybe we should send a note to Dr. Paul.
Well, he emailed me saying it would be too late for him because it's like 11 o'clock in Greece. But if he wants to join, I'm happy with that.
Okay. Let's see, we got a chat.
Next week we'll try and do it for 7 p.m. GMT. Is that okay? And then Paul Lavillette will be happier to join.
Yeah, that'll work.
Justin, you're muted.
That would be 2 o'clock here, right?
Okay, so 7. Well, next week we'll do it for 7 o'clock, 7 p.m. GMT. At the moment, it's just gone. It's just gone 8 p.m. GMT, 9 o'clock London time.
Looks like we lost David.
I think he's just sorting out the audio. He may have restarted the computer.
Okay.
Looking at that Model G1D, I'm wondering if is there any more files other than the CPP file, or is that it?
That seems like it's it. So I'll just read this this note here. So this is what he said about it. It's using the Crank Nicholson solver. That's just good.
Right. I may need some extra code to display the.
Can you speak now, David? Or can you hear us?
Yes, I use the phone now. So
yeah, we can hear you too.
Yeah. So okay, you checked the software I got, yeah.
Yeah, I've checked it relatively quickly.
Yes.
Yeah, it looks very interesting. It looks pretty good because it's much simpler. So
yeah,
something to work with.
I suppose it's also much slower as it is currently. But maybe that's not the problem.
I don't think if we can work with it more easily, then it doesn't matter too much that it's slower.
Okay.
And it will give us something else. It'll give us a different angle, a different method to sort of fall back on.
Yes.
Well, Matt actually did drop that method though because he thought it was too slow, but that was 10 years ago. So computers have gotten a little bit faster since then, and if we got the parallel processing server resources, and we can just pay for faster speed.
David, is this your site here? David Johnson. Okay.
Yeah, this is my account. I also have I don't think I have anything else. I have something that could be used eventually. It's a 2-dimensional solver from 2014, but it's not working as it should.
Okay, well, I'll just quickly, do you want me to quickly go over what I've done? Just quickly show you. So this term here, I realized was actually del G. So I just put that in. I made a note about the exponential time differencing with the Kruger method. So I got some new insights into that. So so down here, this is a graph of how the solver works, how it makes estimates. and I took an excerpt from Wikipedia, just basically describing it. Here we have a function, a function of y, rate of change of y with respect to time, and here is the solver. Here is the approximation of the curve, and it requires values of k, 1 to 4, as shown here. So here we see y plus those values, and so from n equals 0 to 3, we see k1, k2, k3, and k4. These are approximations, and down here is basically what Matt Pulver's written
Great.
as a function solving k0 to k4.
Great. All right.
So there are some. Let me just. So I had to look if we were going to rewrite things. There's these ones. There's this one here, which is just another angle on sort of exponential time differencing for non-linear PDEs. It mentions the paper that Matt sent, which is Cox and Matthews, ETD KR4 method. So we can see here on the Wikipedia, that's what it's called, RK4. There's a more general solution for it down here, and where is it? So one idea I had was when you mentioned rewriting it, I came across this document here, which is Analytical Solutions of Partial Differential Equations. It's just a course in mathematics, basically. But this one here looks even better, which is Partial Differential Equations, Graduate Level Problems and Solutions, i.e. solving the Model G equations. So this one's quite a large document, and it's for people doing exams in partial differential equations. So it's kind of like it goes into all kinds of solutions and methods. Simple eigenvalue problem, separation of variables, eigenvalues, and Laplacian. Quick guide. So it just goes on. It may be useful for solving all kinds of. So that's that. So let's go back to this one here. So that's basically what I had done here. I put in the function that Matt wrote, and connected it with this Wikipedia introduction showing K1 to K4, and this is the approximation of the function, the partial differential equation. Here you can see it's a function of time and distance. And there it is there. So here you can see this is y0. This is the next time step, and they're calculating t1 and t1 y1 here, and they use these approximations to do it. Okay, does anybody else want to talk? Seeing as
It sounds like you're the one who's made the progress this week.
okay.
And I know you're working the most on it.
Well, this was the paper that Matt sent me, and I posted it. Wanted to ask a question. He answered the question here. He said this particular algorithm splits the time stepping into two parts, the Laplacian and the reactions. The Laplacian is calculated more accurately using less points under the Fourier transform, and is transformed back to calculate changes due to the reactions. This overhead turns out to be well worth the cost and was key to being able to calculate in higher dimensions, along with the ETD mathematics. To answer your question, I would have a look at this paper here. So this is the main paper that I think he used. And this is exponential time difference in stiff systems. It mentions solving partial differential equations using time differencing with Krug-Kuta versions. And it's a little, you'd have to read it over a few times to understand it,
Uh-huh.
or to get the gist of it. It probably requires studying in depth.
Yes.
So it says for ordinary differential equations and also PDEs. And it talks about, so we're talking about partial differential equations, and it's basically what I pointed out here. It's basically doing this kind of thing. That you're breaking the partial differential equation. You're approximating it like this, and you're just calculating each of the points. So where do I go now? So can you see here, he's gone from R equals 0 to n reactions. So he's calculating a nested for loop of these values. So it's a bit like it's a bit like calculating these points, doing this many times to get the layout of the solution.
Are those two embedded for loops? I'm not seeing parentheses.
Yeah, there's embedded. There's one there, and there's one there.
Okay. R and N.
I think this phi h. I think this is the this phi h. Maybe this h here. So the y is the phi. I think the h is, but obviously he goes into it more depth. He goes into it. Time differencing. So it's basically he talks about the Laplacian is calculated more accurately using less points under the Fourier transform, and is transformed back to calculate the changes due to the reactions. Okay, so down here he says reactions are calculated here. So the reactions are calculated here, and the Laplacian is not so obvious because its time step is calculated in the frequency domain with the addition of the exponential time stepping technique, and it's done here. I showed you that. So he's saying go to this paper here. So it requires, if we were to use this method along, we could use the other method alongside it if it's simple for the more easy method. But if we were to continue to understand Matt's program more, we'd have to go through this, read it and try and understand it. Let me just see. So this one here, can you see this one? Exponential time differencing methods for nonlinear PDEs. Can you see it's using the same? He's quoted the same guys as the last paper, Cox and Matthews. And if you can see here, so here's like a partial differential equation, and you can see where he split it up. So he's approximating it here. So these are kind of like analytical numerical solutions to that. So this is like the H1, K1, K2, K3, I should imagine. Can you see? This looks like a an approximation. I think this is, yeah. So that's just another a numerical solution, a bit like it involves, it's similar to Simpson's method they mentioned here. Can you see here? Simpson's method is a numerical way of solving integrals. Can you see? So so that the differential equation is equivalent to a simple integral. Then RT is Simpson's, RK4 is Simpson's rule.
So the paper that you think that for you to understand, because you've gone through a bit of this, for you to understand, you think the next step is to go through this Cox and Matthews paper.
Yeah, to go through this and kind of like, you won't understand it straight away, but if you research it, investigate it, and read it over and over again, you'll and basically what it's saying is, on very basic terms, it's basically saying this: we're doing an approximation. We're taking a partial differential equation like that one, and we're doing an approximation. We're doing a numerical solution, and these are the values of k, and we just put them in. We're just estimating the curve at each point and going over and over again to get all the approximations. So this, I think, is more this involves, so that's the what do you call it, the Kutter version. So this is the exponential time differencing. So what Matt has done is he's done exponential time differencing with respect to the Kutter method.
Yeah.
So it requires so I got into a certain amount. It requires reading it and then reading it again, doing a bit of research, just familiarizing oneself with it. So when it comes down to it, it's just a numerical crunch solver for the partial differential equation.
Yeah, maybe it's worth using then if we can know how to modify it.
But the other one's also very good if we get stuck with this one, or we want to do something a bit simpler. Just look at it from a simplistic angle. This one may be more useful for. I mean, it may work out that this one is the best one, but we've got two to work with.
What's this one that you have here? This is the Model G one that we've been working with, right?
No, this is the one that David got from Matt, which is an earlier version, which is much simpler program, doing 1D. So that's all it is there.
So this is this the one we've been looking at, or is this a different one?
This is this is the one that.
Okay, this is the simpler one.
Crank, okay. Using the Crank Nicholson solver.
Okay. All right, the one we've been looking at in the past, the code was a little different. Okay.
Yeah, it was more sophisticated program.
Okay.
Does it include the ability to display the results, or?
You have to speak up, Michael.
Does it include the files for producing a animation? Do you know?
Yeah, I think they're using NuPlot or something like that to, if I recall correctly.
For 1D stuff?
See out.
Yeah. Okay. So NuPlot is a program, open source, that you can include that does 2 and 3D graphing. Go back to the file list, and I think if I recall, I saw a NuPlot in there.
This one here?
No, the more complex one, because I don't see any NuPlot there. I wanted to show you that in the more complex program that he has NuPlot in the file list. If you scroll down, splot. Okay, he's using splot. All right, that's a different one.
You might actually say something about that in the README file also.
Yeah, I think he did. So that's a stat. He's using some type of plotting library, I think. So if you're not seeing that code in that simpler program, he's not plotting it. As it's included here, he's plotting, you know, there's something there to plot with.
Doing math in.
So if you go to the main page for this, where he describes the plotting.
It's not. I mean, it's put up by David the other day, so it's not much about it.
Not this one, the other one.
Okay.
This one. Go to the README or what have you, and scroll down. It talks about the plotting, I believe.
Plotting is just this MK video, making a lot of frames and then transforming them into an MPEG-4 file.
PNG image for each frame.
Where's he getting
On
the
a
images?
plot.
New plot.
Yeah.
Okay, I thought I saw a new plot there. Oh,
Yeah. He's doing some advanced perspectives, since he gets a three-dimensional result, and from that he's choosing a perspective to get the particle image.
So in order to do that, if I recall correctly, I've used new plot before. I think you just dump the data to a file, and then new plot will import that file, and you can put instructions in that file too on how to display things like you know, the parameter, excuse me, the whatever they're called, the
axes.
dimensions, axes, and the dimensions on the axes, and all of that, and the labels, etc., and the labels on the line.
Justin, you said that when you looked at this paper that they did, you said that I seem to remember you saying that you think you understand what the three-dimensional plots were. You said
no, we were looking at standard plotting. Oh, this one.
You said this what x-axis was radial, so it could be 1, 2, and 3 on this axis.
Yeah. Okay. So what it looked like, he was taking sums for that distance away. Okay. So it wasn't that a point in space. It was more of, okay, off of this point that you're, you know, okay, you're getting a point in one dimension, how far away, and then you're saying, well, gather up all of the things that far away from a radius perspective.
Yeah.
And then that's going to be the sum for this point.
For that point, the concentration in, like, say, 3 dimensions for that point, that radial point.
Yeah. So go ahead and get the sum all the way around. Okay. Calculate. Okay. How many geons are here, here, and that'll give you sort of a radius view. So this is not really a map against 3 dimensions. It's a compressed map against 3 dimensions. Okay. Assuming everything's symmetric. Because there weren't 3 dimensions in there.
Well, this program looks very interesting because it's probably much easier to understand. Well, I wouldn't say much, but it looks like it's easier to understand.
Everybody's obviously open to start looking at what they want. I mean, if we want to decide on what we want to talk about, we could, you know, decide this. You've already done a lot of research, and what do you want us to look at? Okay, take your direction.
Well, as I said, I was kind of like I was reading through this and then reading through it again.
All right, so we can talk about going through this paper in more depth.
No, I think it's a similar kind of thing. I think it's similar. I think what I was picking up when I went back to the Wikipedia page,
right,
what it basically is this kind of thing here. It's this kind of like approximating, doing a numerical for one step and then a numerical approximation for the next step.
That was the Cox and Matthews paper is what you're working through right now.
So this one, if you look at it just straight off, it looks a bit confusing. But if you read it over and again, you can see that it's just a analytical numerical approximation for the equation.
So from your understanding, you now understand that one big set of code there with those cases and the for loops, and those correlate with which part of the paper, with its equations in the paper.
So this would be, so basically what we're trying to solve are these X, G, and Y, G, and X potentials, concentrations. So they come from there. Here's the kind of like normalized equation. We want phi G, which is the concentration of G. The concentration.
Okay.
Well, you've got this partial differential equation with respect to time. Okay. So basically, what those equations are doing is they're finding that value. So the time go whatever, they're just like doing an approximation, a kind of iterative approximation to try and get closer and closer to what this value is at each point. That's why it's kind of like a for next loop. He's doing it for each point. Can you see he's going through this kind of loop here, and then another nested loop here.
And and R is the radius that we were talking about before?
R is, well, N reactance, I should imagine that is that goes back to what, let me just have a look at it. That goes back to so the reactance, so he does he solves the reactions here. This is the main part for solving the reactions. Let me just have a look. Let's see. I think it's got, can you see N reactions? So that's the number. I should imagine that's possibly the number of reactions. So in this one over here, so I just go to this one. Okay, so here, these K values, they're part of the coefficients for approximating the solution. You can see them here. Can you see them here? K1, K2, K3, K4. That's the approximation for one point on this plot. If you imagine this is the if this is the kind of like partial differential equation for G or X or Y, he's estimating he's putting some numerical values in like a Simpson's rule, estimating the first one, then he's estimating the second one, and he's eventually he's getting that point, the point, and then he's doing it for the next point, and he's basically, so Simpson's rule, if I can find it, Simpson's, where was it now? Okay, here it is. So can you see it mentions Simpson's rule down here, Simpson's rule. Averaging the 4 increments, greater weight is given to the increments at the midpoint if F is independent of Y. So the differential equation is equivalent to a simple integral. Then RK4 is Simpson's rule. So you can see Simpson's rule is what people use to numerically solve a
So in order to get the point and the vector, it looks like, is it getting a vector there too?
So this is taking this partial differential equation here, which is time with respect to distance, and you're taking this one here. It's going to be, well, you're going to take a point, and you're going to use this equation here, this Runge-Kutta equation.
Runge-Kutta is what I recall from my mathematics professor, or he's a mathematics professor.
Estimating each point. You're doing an iterative process to approximate each point. So that's why he's doing a nested for loop, one here and one here.
So where does the equation fit into there?
What, these ones here?
Well,
phi.
The terms for the approximation.
Let me just see if he's got it in here.
I'm trying to figure that out.
Can you see here? Phi contour. He's got phi contour there.
Yeah.
And he's got phi calc here. And so he's using 5 Maclaurin here and 5 contour here. So let me see here. So phi. I'm not sure if he. Anyway, he calculates phi somewhere. So there's phi here, and I think so. Phi is basically
It's a vector.
is the exons, what geons or yons, the concentration, the potential, I think. And then
And
phi
so-
h is this thing here. I think phi h is the h value, is the, where is it? Can you see
So what's the
f is the potential, and the h is the phi h. The f is the phi.
what is the R and the N
See where the r and the n where
in the code?
in the code?
It's
You
the
mean?
for loops.
That would be reactance, and this is n start to not equal n. So these
Well,
are
he's going through the
these are like
vector.
three-dimensional these are like three-dimensional matrices, I should imagine. So you're solving it like a matrix.
Right, so the n could be the terms of the equation. Is that possible?
I don't know if phi, sorry Michael.
N could be the terms of the equation that it's going through in that vector.
Can we
If maybe all you need to do is just add that extra term to that phi vector.
Because can you see here he's approximating it.
Or phi vector. Phi.
Can you see here that he's approximating it? So he's got y0. You can calculate y0 because y0 is just when time is 0. So it equals that. So you can numerically calculate that. And then when you've got y0, so say y0 is phi, the Etheron potential, then you're doing the next step, you're doing with this h. So
Right, but in terms of the function itself that it's working with, that it's doing an approximation of,
yeah, you're doing
that potential differential equation, those have different terms, and it looks like possibly that differential equation is being represented by a vector.
sorry,
And
represented by what?
a vector.
A vector.
Yeah.
Yeah.
And
So
then if you put
can you see this is a simple? It's like Simpson's rule. It's a
Yeah.
simple. I haven't worked it out 100%, but I got the gist of it. It's like, so this is to calculate one point on the curve.
Mhm.
One point, this point here. And then you've got so you want y0 because y0 is time 0. It's going to be, it's just put in the value. You just put time 0 in there. You get out y0. So he's doing this kind of method, but a bit more sophisticated than this, but along these lines.
Well, what I'm trying to figure out myself is in terms of the actual terms of the equations for the Model G, is it possible that all you have, instead of having to deal with the approximation end of it so much, is just figure out where you can actually alter the equation, the partial difference equation part?
You might have to where the actual equation is. I mean, I think it's spread out within the program. If you alter a part of it, you may have to alter all the different bits of it. If you include a term,
well, okay,
I think you have to alter all the different bits of it that are related to that.
Ah,
Can you see this is the next big one here, which is the so he's called this the exponential time difference, and that's the main title of it. It's just using the Kudda, however you pronounce it. He's just
Runge-Kudda is what I recall the professor saying.
He's using the Runge-Kudda kind of technique within the exponential time differencing. So this when he talks about here, he's talking about the Laplacian is calculated more accurately using less points under the Fourier transform. So using Fourier transforms as transform back to calculate the changes due to the reactions.
But you should only have to deal with the terms once. And then, so you take the Laplacian of those original equation terms, and then you work from there.
But then
But
when he's
there's
using
a
the when
starting
he's
point.
solving the Fourier transform, he's using the Runge-Kudder method. So he's actually solving it. This is what I think. He's solving it by a numerical solution, a numerical approximation, like Simpson's rule.
Mhm.
I mean, if he put in notes and things that make it easier to understand, he obviously did what he wanted to do. But if he had put in a lot more notes, maybe we could do that when we finally understand it. Put in notes. Can you see initialize phi? Now phi has to be the
Where it,
Yeah,
but phi here is like an approximation. So this would be.
okay, so that's using phi. Where's phi defined? We need to
Well,
find.
I think phi. What I think is that phi is a bit like this. Y.
Right, but we need to look in the code to see where it's defined.
Okay.
Okay, I think the main points have been said. I have to leave now.
Okay.
All right, thank you, David.
Okay,
Yeah.
David.
See you.
See you next
Take
week.
care.
So where's phi?
That's a good question.
Because that's, I mean, we're
I mean, you can
thinking
see-
that it's equations in there. At least the
I think the equation is spread out within the code.
well, it might be in this phi, but I'm looking at the. This is
Can you see
the
phi 0, phi n, return. So here's phi Maclaurin. So that's like one.
those are function calls. It looks like, I think, yes.
Here is phi contour.
well, see that real? See the real? I believe that's a vector. And so he's actually operating on that vector, and that might actually be the equation.
This one
Or-
here.
yeah, that's what he's operating on, is that vector called real.
Real
you-
Z. I mean,
You see that all throughout the code, the vector real.
and then we've got phi calc here, which is using phi Maclaurin and phi contour.
So he's doing another operation on the vector real. So
So there's vectors here: D coefficient, RV, RV output. I'm just looking at the definition file, and there's vectors of vectors.
I think it may be explained in this. I think he's given me this exponential time differencing document. Is a fairly biggish. It's a reasonably big document, not too big, but it's quite big. And here you've got the. He thinks that I should read this to understand it better. So this is fourth order methods. Okay, so this is. So this might explain. Let me just have a quick check of that to see if it's got Fourier. Okay, look here. Some Fourier modes, time dependent coefficients. When solving a partial, so we've got a partial differential equation. We want to solve it for phi, the ethron potential. That's the partial differential equation. We've got this one here. We've got this equation here that we've normalized and made into this form. We want to solve it for this. We want to solve that bit. We want to get that bit out for each point in space, and for each unit, for each moment in time and point in space. We want to get those values. So that's the partial differential equation there.
we want to find where that's introduced into the code, and if we know where that's at, then we might be able to alter the program very quickly and simply. If that's how it's done, because once you create that equation, you can then manipulate it from there on out. There's no point to handling it bitwise. I wouldn't see that.
I couldn't find, when I was looking through it, I couldn't find a place where he had put an equation. Can you see phi? Look at this phi. Look, here we go. Phi equals phi calc. You know where phi calc is. So phi, which I assume he's given it, I assume that means potential, ethron potential. Phi equals phi calc. We know where phi calc is. It's in this one. It's in the time stepper, the time exponential time difference. It's down. It's up here. Can you see all this? This is like fast Fourier execute. So he's using. This looks like a function.
To run what happens to 5calc searching for it.
Yeah, 5calc would be interesting.
5calc. So it's up here somewhere. If we can find it. Normalize 5calc. There's 5calc.
There's that real vector again.
And there's 5 Maclaurin that is used in there, and 5 contour.
Okay, so there's actually some definitions of vectors, and I'm not sure how they're used in C, but there's actually C definitions for vectors in one of the files.
5H is 5calc with go on, Justin. So that's.
I'm just pointing out stuff. We're just looking at different pieces of it. I don't think we've put it together. David might be right. Okay, we've gone over the main points. I think we can now, I think it's now, you've given us a lot of information. You've done a huge dump both in the Facebook account and also today. And I think it's up to us to go and try and look. I'm not sure what we're looking for now. I mean, just like last week, we found a few things and then we did a little more search and we couldn't find much more. But you had a good set of questions, and Paul recommended we had sent some questions to Matt, and you did, and you got some response. So I haven't gone through all that. And Michael, have you gone through all the stuff that Brendan has put up on the Facebook?
No, I have not. But I'm not including what we've just done just now. In that case, yeah.
Okay. So yeah, we've gone over some of it now, but I think it's worth for me to dive into it, and I hope I can force myself to have some time on it, so that I at least have an hour into it for discussion.
Well, at the moment, I got a decent amount of time that I can put into it, so I just keep. I didn't notice this here before. I didn't quite notice that there before. Phi there and phi h.
Yeah,
so
that 5calc returns that vector.
That's what I think that is. I think that the phi h is that bit, and the phi is that one. Something
I don't know.
Well, no, it doesn't make any sense.
Like this. This is the
by K, and one of them isn't.
This is the phi, and then the phi h.
No.
Something like that. That's the phi. That's the phi, and that's the phi h. Something like that. I don't know. I mean, I may be wrong on that, but it was something close to that.
All right. Okay. So let's. I'm sort of with David. Okay, a lot's been thrown at me. I think I've gotten something else. What are the big takeaways from your questions to Matt? What were your big questions? You showed a little bit of it. I haven't had a chance to read.
Well, you mean this one here?
Yeah.
The question. So basically, he's saying the reactions are the more straightforward part of the question. So the Laplacian is not so obvious. So basically, he's talking about it's an exponential time difference, and it's basically Fourier transforms. I mean, Fourier back. So he's using Fourier transforms to calculate it. But the Fourier transforms, I think, they are like when he shows them here, they are like functions in C that could just. I've used programs where we use Fourier transforms as a function of MATLAB, and you just put the number in it, and it Fourier transforms it for you. So it does all the mathematics for you just with a function. So you could be using that. And Fourier transforms is quite an effective way of solving problems, solving equations in physics. I'm pretty sure of that. So can you? I don't know if you can see here. Let me see down here. What's this? Time stepper. Anyway, it shows it. It shows it here somewhere. It shows. Can you see that? That there, I think, is a known function. That could possibly be a known function in C++.
I think it's part of the fast Fourier library.
Fast Fourier library. I'm pretty sure that would. And then you just put that function there. You put the result in there. They put the input in there, and it just does the whole thing for the Fourier mathematics for you within C++. You don't have to worry about how Fourier transforms work. It just does it for you.
Mhm.
Because I've come across those functions in C+ in MATLAB where you want to solve something, got a whole lot of big lot of mathematics explaining Fourier transforms. It just what turns out to be a simple function which solves it all for you, you know.
All right.
So I mean, these were interesting things here. So that if one wanted to try and
So this is a Haas-Mendez paper. De la Haas-Mendez. So this is a different paper than the
this is
Cox,
different
Matthews.
from the Matthew Fox, but it mentions Cox and Matthews, and it's using basically this method here, which
Okay.
Matt used. So it's a short paper, but it's showing you. Can you see all these? These are ways of approximating the solution numerically.
Great. Okay. Got it. So that, and then the Runge, okay, and then the Cox and Matthews.
So this is 5. This is what I think is the. I think this is the Ethereum potential, and this one here is just another one along a little bit like this kind of H here. It's a bit like this function and this H. You can see, where is it? You can see down here that where is it? Here, can you see he's using this phi here. So this K here is definitely, I'm 100% sure that is that K there. That K there. And can you see that K is being used to numerically solve the partial differential equation step by step, like Simpson's rule. I'm making a few leaps here, but I feel I'm on the right track.
Okay, it takes time. So you just have to iterate through it. That's normal.
I mean, if we can work it out and understand it, I could put lots of comments in here to explain how it works. And just put it in a different file. Right, there you go. It like with all research, it can take time to get off the ground. You have to play around until you eventually get into it.
Yeah.
And even with this one here, can you see what I've done here? This here. So we could just give that a value and have it changing in 3-dimensional space.
Where are you?
Or we could try and solve it from here.
Okay.
Solve it from, where is it? We could it's that there. We could try and solve this, give this a certain value. So we give this a certain value here and then get out this one here. Or we could just give this certain values. We could just take this one out and give it certain values. So that should be relatively straightforward to solve, a bit like find a numerical solution for that as well. If we just give this
here's the
value,
definition of phi. Okay.
we could just give this a value, like the value of the spin of a subatomic particle, and then find out what this is. And that could be a numerical approximation solver as well. So I was pleased over the last couple of days that it sort of came together. The last 2 days, it sort of started to come together. When I looked at this, I thought, what the hell's going on here? I couldn't. And then I went to I just saw this and it sort of came together a bit better.
Okay. All right. Well, I think that's great. I think you're doing a lot of great stuff. I think you made a lot of progress last week. So I'm gonna start looking at this in a little detail. I'm gonna try and make sure I put some time into this so I am keeping up and can participate and contribute some.
Okay, and I think that was very useful for David getting that simplified one, because that's always something we can go back to do. You
could, but I'm
as well if we want to do more simple.
If we want to, yeah. But I'm trying to get my hands around, what we got now. So yeah. I don't like switching. Okay. even it might be a little simpler. I don't like switching simply because you're just going to be continually.
So switching. Justin, I've got this one up here. I put it on the I've got it in my doc. I've got it referenced in the academic note. So it's down here at the So
Great.
it's down here at the
I
end.
just downloaded that paper, the one you
Yeah,
just.
so you can get it there,
Okay.
and you can just click on that, and it'll take you to it.
Got it. Okay. All right. Thank you.
Okay, Justin and Michael.
Ready to call the meeting?
I've had enough, so I'm going to take off.
How about you, Brendan?
You guys want to continue? Feel free. I've got a lot. You got a lot of stuff there for me to look at, so I'm going to try and dive into it.
So did you find it helpful, Justin?
Yes. You definitely made progress. I think we talked about different things, and I think all of them are valuable. We sort of scaled back to the simpler piece, and you say, well, we can even make it simpler. That's great, but I'm going to try and follow your path that you've highlighted, and try and match up the different things like that phi calc, how those are starting to be filled in. That when I looked at those functions, it does not look like they're equations in there. It looks like there's something else. So I'm going to try and follow you, and I'm going to try and go over first that other paper that references the Cox and Matthews, the De La Hoas, and then get into this one just so that I understand the context where this is coming from. This is more of a solution solving. The other one is using this technique for a specific problem. So
yeah, so it probably mentions like Fourier transforms in here. You just read it and you get a rough idea for it, and then you just use the function, the built-in C++ function to just crunch it automatically without actually having to understand the maths that well.
Oh yeah, that's standard. Okay, great. Okay, thank you. That'll help. So that additional helps. All right. You have an excellent week, and I look forward to talking to you next week. And I'm going to try and open some of this stuff up. You got me more interested in all this, so this is great. Okay.
Okay, Justin. Take care.
All right. Later.
Bye, Justin. Well, I'm just reading over the program here, especially doing what Justin was talking about doing. It seems elusively close. It's just, it's hard to read, but you can feel it's there. It's just a matter of.
Yeah. I mean, it's a question of going over these kind of like looking at the code, this is quite a good explanation of a numerical approximation using computer to numerically approximate the solution.
So he's definitely got a vector
Then just go to this one, read through it. You won't understand it at first, but you just reread it again, look at different parts, and you'll slowly come together. Mm-hmm. And I think that this thing here with this here, he's just what I think he's done is his fast Fourier transform. I think he's gone into here, seen how to do it, and he doesn't need to understand the maths. He just sees that you need to put a Fourier transform here. He's put in the function, and all the Fourier maths is just done for you with this function. So you don't even have to understand the maths in detail. You just have to plug that input in there, and it just does it for you. That's what I think with that.
Well, right, and all these operations, they're in sequence. So if you can get back to the starting point, then there should be a point to where you got to add in that term there, and then it updates the size of that vector, because you're going to have an extra term in your equation now. And
it's just a question of piecing through it bit by bit. You won't understand it all. I don't understand it all at the moment. I got a rough idea of what's going on, and I feel confident about it. And it's just a question of like piecing through it bit by bit until it comes together properly.
Mm-hmm.
I mean, that's quite useful. If you could understand this code, Michael, that'd be a good job. You could put that on your CV and say, "Look, I understand this code," and you'll get a job.
I know. I could probably get multiple jobs.
It'd be good for your science career. Just
absolutely. Well, I mean, you know what Matt's doing now for his career, don't you?
What's that?
He's a programmer,
All right.
professional programmer, so he's very good at this.
Yeah, yeah.
Yeah.
And it's quite a good program to show structure, you know, like a hierarchy, inheritance and hierarchy in C++. I mean, that's fairly sophisticated. That's what programmers do anyway.
Well, yeah, the way he's handled his programming is very, you can tell, at a high level. It's very abstract, and he leverages a lot of coding. Absolutely, and that's why it's so hard to read.
Yeah.
Yeah.
I think the equation is spread out throughout the program. It's not just in one place. That's what I'm picking up. The bits and pieces of the program of the equation, of the partial differential equations, they're kind of spread. I feel they're spread out within the program. So
Well,
you change one bit, you have to change all the other little bits. But once once I get a hang of it, I'll put in comments to explain it more clearly.
Oh yeah, and if I get some time also, I'll see if I can make a little bit more sense of it also. But I that's what I feel. It's really where it's at is it's trying to pin down where does that term come in, and like you said, it could be all throughout the program, but
Yeah.
I don't
You
know.
see the phi there. That phi is obviously the Etheron potential, and this phi h is just a part of the approximation. And if you go here, you
Yeah,
find
look
down
at
here in this
yeah.
one, you find I think I'll find it again. Up here, you can see that I didn't see that before, and now I saw it.
What's that?
You can see that he's doing phi calc. Okay, where was it that
Yeah, and I take it back. That real.
phi calc, here we go, phi. There's phi. And
Yeah.
there's phi calc. So that's one part. That's the important part of it.
So
And
then he's
phi
got the
h,
D
phi
coefficients.
h.
See the D coefficients there?
What's that?
So the base, how he came up with phi was taking a nom2 dt at times D coefficient. So he's got a vector there that he started off with, the D coefficient.
D coefficient, yeah.
And then he's got the nom2 dt, which I'm not sure what that is. That might be another
map.
vector.
I wonder if that's I wonder if that is a C++ function.
Which one? D coefficient?
Hermatian map.
Oh, that could be, yeah, that probably is some sort of function, but the D coefficient and the nom2 dt, that's something he came up with, I'm pretty sure.
Where's that? This one
Oh,
here.
there it is. It's right above. Nom2 dt is equal to, wait a minute, is that the function right there? 4 times m pi times m pi of p. M p, is that right? Or is that phi squared? M phi,
That
M
times
phi?
equals is basically a loop of
You multiply it times itself.
instead of plussing it, instead of a count, it's a multiplier.
Yeah, but is this is not the function itself though, is it?
Now this is phi. This is why I think the
But that's where he gets
concentration that phi is part of, these are approximations of phi. So he's using this to can you see if I
I understand. Well, hold on. I get that. I understand that completely. But that's where he's getting that vector phi. But to get that vector phi, he's using a nom2 dt and a D coefficient.
Yeah.
So it makes sense to understand those a little bit better. And what are those?
Yeah. So should we go to phi calc? We go to phi calc. Here's phi calc. Integer real, integer n, real z. So z is like the length, the spatial dimension, I should imagine.
Yeah, right, exactly.
And
But
he's using 5 Maclaurin. Maclaurin is like it's a bit like a series, isn't it? A mathematical series, I should imagine.
Yeah, but that real z, and
the Maclaurin is up there.
that real z, that is a vector that is formed by the product of those two terms that we were just speaking about, the nom2dt.
Yeah.
Yeah, that's the real vector. Nom2dt
Right.
times d coefficient of a vector of r amount of
And this n,
terms.
this q quote here, summation
Yeah.
map.
So I think it's in that for loop that he actually comes up with
He
some of
gets
the
this one.
equations.
He gets this one out here. So that goes in there.
Ah.
And,
But and then he's got, so it basically kind of like working backwards from there.
yeah. It's just a question of like stepping through it, just giving it a break, and then going back to it, and just kind of like read this to get a better you won't understand it straight away, but if you reread it several times and read different bits of it, and then going to places like here to sort of like understand the basics of the Runge-Kutta method, and it'll start to piece together, and then you can probably go to these ones here. Where is it? This one here. This is a short paper, so it's basically they're numerical solutions. So they're solving it by the number crunching method instead of solving it using mathematical skills. Then solving it by number crunching, by just breaking it down and getting the computer to go through lots of loops to as an iterative method of solving it.
Right. Yeah. Well, if I find something that looks promising, I'll forward it on to you, Brendan.
Okay.
Yeah, because that's one thing you did a good job of today for sure. If amongst all the other things, is getting us more interested. I think it's because we're getting closer to the.
Yeah. I mean, it may be that we understand, we get stuck, and then eventually, and then you just work through it, and you get on to the next bit, and then you understand it, and then you come across something else, and eventually you put it together.
Yeah, that's it. Yeah, it's cumulative. Absolutely. Well, thanks again, Brendan. Awesome work, and yeah, and same thing with Dave. I know he's not here right now, but that it was great that he got that 1D solver. That could come in handy for a number of things.
Yeah.
Yeah. So, well, have a great evening, and we'll keep in touch.
Okay, Michael, take care. Bye-bye.
Yeah. Enjoy your evening on the other side of the pond.
Okay.
Bye.
Cheers.
See you.